Okay, thanks everyone for coming to my introductory video to my poster titled as Extended Differential Covariance Recovers Ground Truth Connectivity in Multi-Scale Neural Systems. In the following 5 minutes, I will walk you through this novel functional connectivity estimator, which combines a dynamical view of neural systems and show the robust performance in simulated systems across multiple neural computation scales. First of all neural systems we encountered could be treated as nonlinear, either nonlinear or linear. To be more specific, most nonlinear systems can be described by this differential equation on the left, where x is the state variable, usually some sort of neural recording, and A is the connectivity matrix of interest. The nonlinear function fx here is an arbitrary function. Depends on the specific system. And regardless of the nonlinearity at single neurons, at microscopic level, neural activities can be characterized by a linear system because of the ensemble effect. And we argue that this general view of neural dynamics would help us develop a robust functional connectivity estimator. And we term this estimator as extended differential covariance. Let's look at the derivation process on the right, using the linear system as an example. Here's the system equation. If we perform the outer product operation on both sides of the system equation and average over all time points, then the outer product of the signal and its with itself is just the covariance matrix, provided that it's centered. The outer product of the derivative signal with the original signal was termed as differential covariance from our previous work. To obtain an estimate of the connectivity matrix A, we simply multiply the inverse of the covariance matrix. In this way, we obtain a linear estimator of A, which I termed as delta L. As for the nonlinear case, the derivation is similar. The only difference is we have to choose a nonlinear function, and there's a lot to choose from. And we decided to start from the simplest one, the ReLU function, and I term this estimator as delta ReLU. As a proof of principle example, the estimators were tested in several 3-neuron motifs as shown here. Here is a confounder motif and here is a Chen motif. In both motifs, the solid black lines indicate true connections and the dashed red lines indicate some false positive connections. And the estimator results are shown here. Both estimators pick up the real connections and explained away the false positive connections as shown in both motifs. Then I reached out for a more realistic neural model, that is the leaky integrate and file network. I quantified the method's performance based on their ability to recover the existence of ground truth connections. Such process was summarized by an ROC curve for each method. Compared to the two benchmarked methods, the covariance method, the covariance matrix and the partial covariance matrix, both estimators delta L and delta ReLU have superior performance, while the nonlinear one, delta ReLU, is the best among them. Lastly, I turn to a microscopic brain surface model supported by DTI measured anatomical connections. And the estimator performance was quantified by C sensitivity shown on the right. Both delta L and delta ReLU outperformed the two benchmarked methods, and delta L is better probably because of the ensemble effect mentioned before in the previous slides. In summary, extended differential covariance estimators started from a dynamical view of neural systems. It produces reliable estimation performance across multi-scale neural systems. In addition, the potential of the nonlinear estimator is big because it can adapt to different neural recordings by choosing the nonlinear function wisely. If you are interested, please come to my poster session on Thursday.